In this video, we will look at the connection between frequency modulation, which is standard in electrical engineering, and use that to derive a Bessel integral equation, and that opens up the connection to a lot of problems. So frequency modulation is, or phase modulation is where you put the information in the phase or in the frequency. So this is phase modulation. If this term is replaced by integral 0 to t f tau d tau, that's phase modulation with some suitable constant. And so to analyze this, we will look at, let's say, a single tone. In fact, so ft is here sine b naught t. To see what's the bandwidth of, so remember this is now phase modulation, or by putting a cosine b naught t here, you can also get this expression. So it's, you can interpret it as fm also. So the question is, what is the bandwidth of this in the frequency domain? How much band, and where are the frequency components, etc. So the easiest way is to rewrite this as the real part of j omega naught t plus beta sine b naught t, and this we can split it as two components. Real part of e raised to j omega naught t, e raised to j beta sine b naught t. So this is easy to understand, so let's concentrate on this term. So if you take that term e raised to j beta sine b naught t, that can be expressed as, this is a periodic function with the period b naught. So it has this expansion, and so the period is 2 pi over b naught, and the ck's are 1 over t minus t by 2 to t by 2, and e to the power j beta sine b naught t, and e to the raised to minus j k b naught t dt. So if you put this together, this is b naught over 2 pi minus t by 2 to t by 2, which is pi over b naught. E raised to j beta sine b naught t minus k b naught t dt. So if I make a new variable x b naught t, then this reads, so x is b naught t, so dt is dx over b naught. So b naught cancels, 1 over 2 pi, and when x is, t is minus pi over b naught, this goes from minus pi to plus pi, e raised to j beta sine x minus kx dx, b naught cancels. And this has got two parts, cosine and sine. The cosine is this is an odd function, cosine is an even function. Integrated here goes to, and the other part is, the imaginary part is an odd function. If an odd function integrated, that goes to 0, because this is cosine of this plus j sine of this. This is odd, so that integral goes to 0. So the integral is only is real, and it's only cosine of this exponent. And because it is even, it is twice the integral from 0 to pi. So we get this expression. because cosine is again an even function, we can rewrite it in the standard. And this term is jk of beta, Bessel function, kth order evaluated at beta. So this has the standard properties. This is minus 1 to the power k, j of minus k beta, etc. What I want to do is derive an a differential equation for this is so usually this is the electrical engineering part. So to complete here, this part can be replaced by sigma jk beta e raised to jk b naught t. From here I substitute it. So if you put everything together, this simply reads jk of beta cosine omega naught t plus k beta naught t. So if you want, you can rewrite this as k goes from minus infinity to plus infinity. What I am interested in is developing a, this is again all standard stuff, but in this context, developing a differential equation for a jk, because then that opens up its connection to all sorts of other problems. So generally in electrical engineering, this is the way things are analyzed. So from it to complete this argument, this line of thought, so we will see that even though the original signal is just a single tone, this is the transmit signal here, a Fourier transform of sine b naught t or cos b naught t. When you do the FM, there are lots of components. In fact, all components around omega naught. So it occupies a decent bandwidth on both the sides. So this is omega naught minus omega naught. This is omega naught plus k beta b naught, etc. So roughly the bandwidth is 2 times beta plus 1 multiplied by b naught, approximately 98% of the energy. The whole point is, even if you are transmitting a single tone, the disadvantage of FM is it takes a finite bandwidth, but the advantage is the noise cancellation is by a factor of beta cubed. I'm not going to go over that, but that's the whole point of using FM. But today's job is to develop a differential equation for j beta. So since we are taking derivative, instead of beta, let me bring in the variable x. So instead of beta here, I'm going to replace it by x, a new variable. And I want to, so so this is 1 over pi either way, 0 to pi cosine of nx minus, so I'll use some other way, since I used x there, n theta minus x sine theta d theta. That's y of x. So y, of course, we can write it as so let me do dy by dx. So that's going to be here. Derivative of cos is minus, so that's minus 1 over pi, 0 to pi. Derivative of this quantity with respect to x, so that will be sine theta, sine x, sine x. So we need some of these equations later. And I'm going to do the derivative of this again with respect to x. So it's a second order differential equation. Again, it's a standard equation. My point is to derive it from this definition. From the trigonometric expression, I want to go to the differential equation. So this will be my derivative of sine is cos, so this minus will stay. This is 0 to pi. Derivative of the inside quantity with respect to x. So that will be sine squared theta cos x sine theta minus n theta d theta. But sine squared theta, I can write it as 1 minus cos squared theta. So this will be minus 1 over pi. The first term is 0 to pi cosine of x sine theta minus n theta d theta. But notice this is just y, minus y, the whole thing. Plus 1 over pi integral 0 to pi. So minus minus plus cos squared theta cos x sine theta minus n theta d theta. So let me call this expression 3. So if you go to this expression, you can rewrite it in this form. So you have minus sine theta, that's the derivative of cos theta. Then I want to use the UV rule. So that's the same as 0 to pi 1 over pi. So now if I use u dv is uv cos theta sine so when theta is 0, this is 0, sine 0, 0. When theta is pi, is also multiple, this is 0, and this is multiples of, or here, when theta is pi, this is 0, so this whole thing is 0. And the next term is minus 1 over pi cos theta cos x sine theta minus n theta multiplied by the derivative of that quantity with respect to theta, so that will be x cos theta minus n. Derivative of this quantity is cosine of this multiplied by the derivative of this, all with respect to theta, so multiplied by d theta. Derivative of this is x cos theta minus n, so that part is good. So remember, this integral is with respect to 0, or with respect to theta, so the x comes out. So minus x multiplied by 1 over pi 0 to pi cos theta. I'm going to write two terms. So there is a cos theta here, so cos squared theta cos of x sine theta minus n theta d theta plus one more term. The other term is minus minus plus n goes out, so 1 over pi 0 to pi, n goes outside, so that is cos theta cos x sine theta minus n theta d theta. Okay, so that's just a dy by dx. Now if I, bear with me a minute, but let's do, so because I have an x here, I'm just going to bring this 1 over x here, because then you can do some simplifications. So this x goes away, so this is minus 1 over pi 0 to pi cos squared theta cos x sine theta minus n theta d theta plus n over x, because I pulled out an x there, 1 over pi 0 to pi cos theta cos x sine theta minus n theta d theta. So let me call this 4. So interesting is, if you look at 3, you have this same expression here, but with a plus sign. So this, if you add this to this will cancel. So that's where I'm. So let's do, the next step is to do 3 plus 4. Generally, to connect these two, because generally if you go from the trigonometric way, especially electrical engineering or communications, if you come from the frequency modulation, you do come up with the Bessel coefficients and their expression, but that's a trigonometric expression. It's not easy to see the corresponding differential equation. In any case, let me do 3 plus 4. So that's d squared y by dx squared plus 1 over x dy by dx. For those of you who know the Bessel differential equation, you can see this is the way the terms go. That's the reason I'm sort of picking them up. But in d squared y by dx squared, you also have this term, minus y. So I'm just going to bring this to this side. In other words, here the actual expression is d squared y by dx squared plus y equals 1 over pi 0 to pi cos squared theta cos x sine theta minus n theta dx. So this is actually 3. So if you add 4, this term will cancel with this. So this term plus this term is from 3, this is from 4. Is n over x 1 over pi 0 to pi cos theta Okay, so now I'm again, because of the Bessel differential equation, there's an x squared term, so I'm going to make this x squared. So all I have to do is multiply by an x. So I'm going to write the right side as n over x squared, 1 over pi Alright, so that's the FM. So if I couple this together, this reads now n squared over x squared. This n comes here. 1 over pi cos x sine theta minus n theta d theta. But you can see why I introduced the n, because this is now same as what we started with, this whole quantity. So that's why. So we took care of this term, so that's why. So if you look at here, the first term is n squared over x squared, 1 over pi this quantity, this is y, and the remaining term is n over x squared in 1 over pi integral 0 to pi x cos theta minus n from here, then multiplied by cosine of x sine theta minus n theta d theta. So we need to evaluate this integral, and this itself is, you can see that if you call this to be, remember this integral is with respect to u, so if you substitute this to be u to be x sine theta minus n theta, then du is x cos theta minus n. So x cos theta minus n multiplied by d theta is dx. So this integral actually turns out to be this integral will go to, again the limits are the same, you can see it will be simply cos u du. 0, it is 0, and pi, it is n pi. And integral of cos u is sin u. At those limits it's 0. So this integral will turn out to be 0. So the differential equation, interestingly, will come d squared yx by dx squared plus 1 over x dy by dx plus this is n squared over x squared. So plus 1 minus n squared over x squared multiplied by yx equal to 0. So this in general is, so that's the differential equation we are looking for. This is the Bessel differential equation. It's also written sometimes as multiplied by x squared, so x squared d squared y by dx squared plus x dy by dx plus x squared minus n squared multiplied by y equal to 0, whose solution y is jn, y is jn of x. So the interesting thing is, starting from this electrical engineering viewpoint, frequency modulation, and showing that the coefficients are Bessel coefficients here, k from minus infinity to plus infinity. This jk beta also satisfies this differential equation. This opens up a connection to all sorts of other problems in astronomy, mechanical engineering, and so on. For example, a loaded spring or a decaying spring will turn out to be, in terms of the Bessel function, the solutions. So this is the main result I wanted to show. So as an example, so the key is here, so in our place, of course, I replaced beta with x. So you can see the connection. This jk beta also satisfies this differential equation, second order Bessel differential equation. For example, if you take a spring, there actually the force is proportional to minus kx, how much you have stretched with So this leads to a second order simple differential equation, a d squared y by, let's say y. dt squared plus k over m y equal to 0. So y is some constant cos omega naught t plus b sine omega naught t, where omega naught is square root of k squared over k over m. So this is the standard equation. Now if you assume in this differential equation that there is also a decaying term, in other words the spring gets with age the component decays, etc. And then we have this differential equation, d squared y by, I did this earlier, omega 0 squared e raised to minus aty. So this is not easy to solve. With a simple change of variable, something like this, so we are going to look for a solution in terms of u. So we want the dy by dt is dy by du multiplied by du by dt. So du by dt is from here minus a by 2u, and multiplied by dy by du. Next we want d squared y by dt squared. So that is d by du of dy by du multiplied by du by dt. So that is minus a by 2u, and derivative of dy by du with respect to, that is this quantity with respect to u. So one more minus a by 2 will go outside, so that is a by 2 the whole squared. Derivative of this with respect to u is dy by du plus u d squared y by du squared. So if I substitute all this into this equation, so this will read now, say this is 1a, or this is 1, this is 2 and 3. Then 1 reads, so d squared y by d2 squared is this a by 2 the whole squared, u squared d squared y by du squared. Then you have u dy by du from here, and we have this term, and so that's d squared y by dt squared. I just substituted here, number 2 went here, and this quantity is in terms of u. So from here you have omega squared e raised to minus at. So you square this, is a squared by 4 u squared. So a squared by 4 is outside, so this is u squared y equal to 0. So this leads to this differential equation, u squared d squared y by du squared plus u dy by du plus u squared y equal to 0. So y is j0 of u, and u is j0 of omega naught 2 over a e raised to minus at by 2. This is also, if I remember, cosine of something over argument divided by square root of x. So close to cosine, but not exact. It's the So the whole point is, you can connect this to the FM also. So the whole point is, starting from here, we are able to derive the standard differential equation, which of course has opens up lots of connection to a lot of problems in mechanics. And that's what I wanted to say.